We bought supplies. Alright, so with the rangefinder, at this mass,
69 yards and -5 degrees. -93 yards, -4 degrees.
so
101 yards, -3 degrees.
we have 3 masses, and we use mass 1 to find the amount of energy that is being used in the launch, so that we can then compare it to mass 2 and mass 3, so we can use projectile motion to find mass 2 and mass 3, or to estimate them. So looking here, we can see the trajectory. Each mass is shot at 5 degrees upwards, and we used a rangefinder to find the direct distance in which it landed and the angle. We have this equation, which is seen here, and it can be used to find the initial velocity. So plugging in our numbers, we get 40.33 meters per second. And assuming that each mass is shot with the same energy, we can find energy by plugging it into the 1/2 mv squared equation, kinetic energy, and that gives us 67.09 joules. All right, and here looking at mass 2, we can see the projectile motion. The direct distance is 85.04 meters. It goes downwards at -4 degrees. So we use this equation again, plug in our numbers, and we find that the initial velocity is 49.78 meters per second. So using that, and assuming that the kinetic energy is the same as mass 1, we can plug that into the kinetic energy equation, 1/2 mv squared, and we find that mass can be estimated to be 0.0541 kilograms. And so if we compare that to the actual mass, which was 0.0617 kilograms, we find a percent error of 12.32%. Okay, and for mass 3, we can see the trajectory again. The direct distance is 92.23 meters. It goes downwards at -3 degrees. Again, using this equation, we plug in our numbers and we find that initial velocity is 54.99 meters per second. And assuming kinetic energy is constant through every launch, 67.09 joules, we find that mass is 0.0444 kilograms. And so the actual mass is 0.0417 kilograms. We find that the percent error is 6.47%.